Okay, so in this lesson, we're going to learn about linear combinations of vectors and how linear combinations of vectors relate to systems of linear equations. And a key concept we're going to focus on is the span. Okay, so that word span is going to come up over and over this semester. So take the time now when you're reading to really understand what that means. Okay, so if we have two vectors, u and v, u is going to be 1, 0, 0, and v is going to be 0, 0, 1. If I compute 3u plus 4v, so that's going to be 3 times 1, 0, 0 plus 4 times 0, 0, 1. To multiply a vector by a scalar, right? A scalar is just a plain old number, right? To multiply a vector by a scalar, you multiply every entry in the vector by the scalar. So this is going to become 3, 0, 0 plus 0, 0, 4. And then to add vectors, you add component-wise. Add the first entries, add the second entries, add the third entries. So this becomes 3, 0, 4. So we multiplied u times a scalar and v times a scalar, and we added them together. Doing that is called taking a linear combination of the two vectors, right? When you multiply each one by a scalar and add them up, that's called a linear combination. Okay. So another example of a linear combination would be if I picked two different scalars, right? So if I did 7u plus 2v, right? Just pick random scalars, and when you add them together, right, we're going to get 702. That's another linear combination. Because there are infinite scalars to choose from, and you just pick them at random to make a linear combination, there are infinite possibilities for building linear combinations of two vectors or more vectors, right? You can also take a linear combination of 3 vectors, just pick 3 scalars, add all 3 together. So we have a name for the set of all possible linear combinations, and it's called the span. Okay. So the name for all possible linear combinations is the span of u and v, right? So that's where we build a set that contains every possible choice of scalars and adding them together. So give me another vector in the span of uv. Pick 2 scalars, throw them on u and v, add them together. 101, sure. If you just put scalars of 1 on them and add them together. So that would be 1u plus 1v, 101. There's another vector in the span. So if I want to describe the span using set builder notation, okay, these 3 vectors that I've written down that are all in the span, what do those 3 vectors have in common? They all have a 0 in the middle. So I can use that to describe this using set builder notation. So I would say, well, it's the set of all vectors that looks like something, 0, something else, such that a and b are elements of the real numbers. Okay. How many vectors are there in the span of u and v? Infinite. Yeah, you can pick any a and b, so it's infinite. Any real numbers a and b. Is the span of a set of vectors always infinite? So in this case, it was infinite, right? Is there any way it would not be infinite if I picked? Yeah, if 0 is the only vector, then there's still an infinite choice of scalars, but it doesn't change your vector. Yeah, so almost always, right? almost always you have an infinite number of vectors in the span, unless you're looking at the span of just one vector, a vector full of zeros. Yeah.
You be balanced with a
As in they just can't be any real, but they'd have to be a real between, yeah. It actually would still be infinite because there's still infinite real numbers between on any interval. Yeah. And the definition of span is that you can choose any scalar in the real numbers. Yeah. But if I was just defining a set, like it wasn't a span, yeah, you could make it not infinite. Yeah. Is the zero vector always, sometimes, or never in the span of a given set of vectors? Yeah, so if I give you two vectors, let's talk about the two vectors that I did earlier, right? U and V. Can I find scalars that I should put on those and so that when I add them together, I get 0, 0, 0? 0. Yeah. If you just take both of your scalars to be 0, when you add them together, you'll get the 0 vector. So the 0 vector is always in the span. So I'll write always. Just take scalars, I should say take all scalars to be 0. And then when you add everything together, you'll get the 0 vector. All right, so here are 3 questions that all mean the same thing. So this is just some vocabulary. Is 4, 12, 4 a linear combination of 2, 1, negative 3 and 6, 5, negative 7? So they're asking, are there scalars that you can put on these two guys and add them together that you can get 4, 12, 4? So I'm going to write that down. I'm going to translate that. If it's a linear combination, that means that I can put scalars on those two and add them together and get that. So I could say 2, 1, negative 3 times some unknown scalar, we'll call it A, plus another scalar times 6, 5, negative 7. Is there an A and B that I can do, that I can put on those two to build 4, 12, 4? Has a solution, right? If that has a solution, if there's an A and a B, then yes, it's a linear combination. Another way of asking the same question is 4, 12, 4 in the span of those two vectors? Same thing, because being in the span just means it's a linear combination. Same question. And then a geometric way of asking that question is asking, is 4, 12, 4 contained in the same plane as 2, 1, negative 3 and 6, 5, negative 7? So those two vectors in R3 form a two-dimensional plane. Any linear combination of those two vectors will lie in the same plane. So let's just answer these, right? Is there an A, a B, and a B that will make that vector? Okay. So let's simplify what that says. That says, remember that when you multiply a vector by a scalar, you multiply every entry by the scalar. So this is 2A, A, negative 3A, plus 6B, 5B, negative 7B, equals 4, 12, 4. I'm being lazy with my brackets just for time. Now I'm going to add things component-wise. So this says 2A plus 6B has to equal 4. And A plus 5B has to equal 12. And negative 3A minus 7B has to equal 4. So now I have 3 equations with 2 unknowns. I can set up a matrix and row reduce it to solve. So see, is there an A and a B that makes this true? So this is going to become 2, 1, negative 3, 6, 5, negative 7, augmented with 4, 12, 4. And then I'm going to do some RREFing. I'm not going to do all the workout now. We've had some practice with that today. And I will just tell you that this comes out to 1, 0, 0, 3, 1, 0, augmented with 2, 5, 0. So I shouldn't say RREF because I didn't go all the way, right? RREF would mean I also eliminate that 3 to do the backwards phase. But I just did the forwards phase to tell if it was inconsistent, right? Is this consistent? Yeah, yep. So y is 5 and x plus 3y is 2, so you can solve for x. Or a and b, sorry, yeah, not x and y. So yeah, this is consistent. We don't even care what the a and b are because the question was just, is it or isn't it? Yeah. So this is, there is a solution, so the answer is yes. These two vectors, there is a linear combination of those two that makes 4, 12, 4. Right, so if I finished, right, I would get A is negative 13, B is 5. And those are the scalars you would use to build to make the linear combination. All right, so that's it for the lecture portion of 1.3. When you come back on Tuesday, we'll start with the activities on page 23. You do not have to do those before you come back. We're going to do them in class on Tuesday.